Okay, there we go. Okay, so in this lecture, we're going to focus our attention on qualitative observations, more so than quantitative observations. So we've had a lot of discussions about numbers so far. We'll definitely return to numbers, but now we want to be able to just as clearly describe matter qualities. And the reason being is that uh, the reason being is that we want to distinguish matter through our qualitative and quantitative observations and use these observations to make judgments about matter. Remember, part of the reason why we write things down so diligently and carefully with, say, significant figures is so that we can make accurate predictions or draw valid conclusions about matter. It's not going to be beneficial if we're not being careful about how we describe matter in every sort of way. So that's sort of where we want to focus our attention. How do we qualitatively describe matter? And so this slide will be familiar if you saw the pre-lecture, hopefully you did. It was a short video on the phases of matter and how chemists perceive matter. And it all draws from the particulate theory of matter. And by the way, that pre-lecture is in the synchronous lecture page. So it's with all of the other lecture materials. All matter is made of small specks or particles, right? So that's the basic idea, is that to understand the world around us, we need to understand the smallest picture just as well as the big picture, everything we see around us. And so we say as chemists that matter is made of particles. And just to give a visualization, if you spray, a mist bottle or a water spray bottle, you can see that even though water was once looked like a continuous liquid, we actually see it turn into little specks. And in fact, the specks we're talking about are much smaller. And the example I show is this image. This is one of the first real images of the particles we're going to be talking about, molecules and their atoms. But what we can see is that the scale, according to this image, is very small. It's 5 angstrom is how we pronounce this. And the conversion factor for that is actually 1 angstrom is 1 times 10 to the minus 10 meters. So an extremely small scale is what we're talking about, but that's the power of chemistry. It's being able to make conclusions from both sides of the perspective. We can, by understanding the bigger picture of matter, so all of the things we're going to talk about in this lecture, we can start to tease out what's going on to the tiniest little specks of matter. And then later on in the course, we're going to zoom into that small scale and say, well, if I know this information about the particles, that I have this many atoms and molecules sort of joined together, I can then make predictions about, well, I must know something about that substance as a whole. And we'll be able to do that when we talk about these particles and make sort of conclusions about, well, I might know something about its properties. So this substance might be very sticky, or this substance might have a low melting point and things like that. So that's where we're getting at. To understand the big picture, we need the small picture. Now, I've already mentioned these words, so I should be careful to actually define them. So our tiniest of tiniest particles that make up the universe are atoms. So particle itself is a generic placeholder term. We use it all the time. But when we're talking about the specks that make up the universe, we're referring to atoms, and they're usually depicted as dots on paper. And sometimes atoms join together. We say they bond and they form molecules. And so there's a sort of visual cartoon depiction of this molecule that's being imaged. And we see that the atoms are the circles, and they make quite an interesting and beautiful sort of geometric pattern. It looks like hexagons, right? Like we learned in geometry class. Hexagons joined together. And so there are 2 different types of atoms here, color-coded, a gray and a white. But that's the goal that we're setting for ourselves, to be able to have conversations about these tiny specks and be able to make predictions with them. Just to give us an analogy of how this works, one way we can think of it is that atoms are like the letters of our universe, right? Everything is built off of atoms. So these tiny specks build everything that we see, we feel, we sense around us. But just like how we can discuss letters by themselves, some letters are okay by themselves, most of them combine to make words. And when they do, they make substances, or they make, you know, a word that has a different definition, right? Like MOM, those are all letters, and by themselves, they don't really have much to say. But if I put them together, they spell mom, and mom has a new definition. It has something that I might perceive in my mind, or you might as well, and so forth. In the same way, we say that our alphabet of atoms can join together in different ways to make new substances. So in this case, we're depicting one atom that we're going to call H for hydrogen, and another type of atom that we call O for oxygen. When they join together, they make H2O. And that itself has a new, you know, using the word analogy, it has a new definition. Water is different than the hydrogen and the oxygen that it comes from. It has new properties. But in order to have these conversations, we need to zoom in on the small picture and be able to understand what's going on with these particles. And of course, stop me if, oh, before I go on, well, let me finish that thought. My first thought is at any point, the chat is open. So if you would like to ask a question, please do so. It's oftentimes very beneficial for us to sort of get those questions answered right now. The other thing I mentioned, I will mention is that the discussion on the phases of matter, I know a lot of us have experience, you know, knowing what gases are and liquids. So those lecture slides are still important to know for upcoming quizzes and exams, but I'm not going to talk about it here. I talked about it in the pre-lecture video. So those slides that, you know, were part of that, those are still important. But what we should have gotten from those slides, I'll just sort of shortly summarize them, is that when these particles that make up our universe come together, the behavior as a group reflects what we consider are the phases. So we should be able to identify what the particles are doing based off of what phase of matter we have, and vice versa. So if I know that this substance, say air, is a gas at room temperature, what does that mean? Well, it means that those particles are far apart, flying in all sorts of directions, and they really have no attractions to each other. So they stay far apart. Whereas, you know, I don't know, maple syrup is a liquid, but it's really sticky, right? So it must mean that the particles are closer together. They don't really have as much room to move around. And they must be very sticky for one another. And we'll go into more detail about what that means, what stickiness or attraction means. But that's the basic idea I want us to get with the idea of phases of matter. What can we learn about the small picture from the big picture? Just because something is a solid, what does that mean about what's going on the tiny scale? And then flip it, vice versa. So reminder, that is in the module in synchronous lectures. So chemical particles, I kind of teased that they're really tiny. How small are they? 1 drop of water contains 10 to the 21st power water molecules. So to remind us what this number means, it's sometimes hard to sort of imagine in our brains what a number like this is. But just to remind ourselves with scientific notation and which is important to know right now, that this means there are 21 zeros in this number. So it's the number 1 with 21 zeros, because again, it would be moving the decimal point that many times. So 1 times 10 to the 21 is going to be moving that 20, and I won't even write it. That's a huge number. So imagine that number is referring to how many water molecules are inside a single drop. So that just emphasizes that we're talking about things that are really tiny, And even in very small samples, maybe small amounts of matter, we have a lot of particles. To contrast that, there are only 10 to the 11th power pennies currently in circulation. So there are actually quite a few more water molecules in a single drop than there are, coins. Probably all coins put together wouldn't come close to this number. Maybe that's an exaggeration. I would have to sort of think about it. Probably it's getting there, right? Because particles are so small and because we can have so many of them in a single drop of water or anywhere, we use a special unit to discuss particles, and that's called the mole. So because matter is made up of small particles, chemists use the word mole to describe amounts of matter. So in words, and to use an analogy, and I've been looking through your Pogles, and I see we're getting used to the idea of putting together conversion factors. The mole conversion factor is a little bit tricky, I will admit. And so I like to emphasize to students that if it's ever confusing what we mean when we say mole, I use the idea that the mole is another way to say it is a chemist's dozen. So much like a baker might be talking about, I need to make 3 dozen cupcakes. We understand that, well, a dozen means a group of 12, right? Or a dozen eggs are needed for this recipe. That's what we're talking about with moles, because atoms and molecules are so small and there can be a lot of them in a small amount of space. We say, well, I'm not going to talk about individual counting the numbers. I'm going to talk about groups. And our group is called a mole, and it's equal to a special number, which is written here. However, in scientific notation, it's 6.022 times 10 to the 23. So this is quite a large number. If we sort of take a moment to count the zeros, I believe this comes out to, what is it? So a group of, this group of zeros is equal to a billion. This group of zeros is equal to another billion. And what by that I mean 10 to the 9 and 10 to the 9. So we're talking about 600,000 billion. Sometimes you hear people sort of write numbers in terms of like, this is a million trillion. They're talking about how many zeros there are. So it's the equivalent to having the zeros of a billion, another billion, and then 100,000. So a lot. But again, that's what makes this idea kind of weird and a little bit frustrating for students. It's because it's a number that's really hard for us to grasp mentally. There can be a disconnect in what we're talking about and how to use it. So I really want to emphasize that little trick that I'm mentioning. Think of the mole as chemist's dozen. When we're talking about a mole, we're talking about a group of counting things. Much like we're to say, when I have 3 dozen, it's actually 3 groups of 12. When I have 3 moles, I have 3 groups of this number, which is a huge number. Right? So that's what we're getting at. We're going to want to talk about particles, and to do the math with particles, we might need to count how many there are, and that's where we use a special unit that comes from chemistry. And oh, good point made in the chat. Does this number have to do with Avogadro's number? That's actually the name that we give to this number. In fact, it's on the next slide. Avogadro's number. So perfect segue. Thank you. So why is it called Avogadro's number? It's because the scientist who studied this well, he didn't study this in particular. What he did was he was very fascinated with gases. So he was I believe he was Italian chemist in the, way back. I would want to say the 1500s, but I'm not sure. Maybe 16. His name was Avogadro, and he was studying gases. what he found was he was thinking about why gases expand and contract. You can blow them up bigger. You can make them shrink if you put them in ice, make them cold, and so forth. So he studied gases very carefully, and he came to a conclusion that in order for gases to have all of these properties and behaviors, it must mean that there's stuff inside the gas, even if we can't see it. So air looks invisible to us. We can't see air, but there must be something in air that causes a balloon filled with air to do stuff like shrink, like get bigger under different conditions and so forth. And so he said there must be particles, and he actually did experiments that proved that the number of things in a certain, a number of things that, you fill up a balloon are equivalent to this number. And this number comes about several times in this class. So this is our first instance in sort of getting with it. But one of the most important things about this number is that it's a relationship. So I've written it as sort of the starting point to create a conversion factor. Whenever I have a mole of something, it's equal to this number that we call Avogadro's number. You'll notice the word things there, and this is probably the most confusing part of doing math with the idea of moles. It's that we have to substitute for the specifics of the question. It's not like milliliters and liters where we don't have to worry about changing the wording of the units. And in this case, we do. And I realized that on the POGL, there was one question, the last question, that kind of throws students off. It's the question on if a beach has this many moles of sand, then how many grains of sand are there? And so it takes a little bit of an extra step because we have to rationalize, well, the things that I'm counting are grains of sand. And so I would say 6.022 times 10 to the 23 grains of sand is equal to 1 mole of sand. And that's where it gets a little bit weird, because it's not that the math is any different. It's that sort of like the English language kind of gets in our way, because we have to recognize that we're not actually going to, grammatically, we're not going to substitute sometimes things the same way. Because I would say grains of sand make sand. And so we just have to be careful with the fact that sometimes the wording of how English is kind of set up can throw off what we should substitute here. And that was like an example of that. And I'd be happy to go through an example of doing that. But one thing that I would like to focus on is that much like any other conversion factor, we create fractions to do the cancellation, to turn one unit to the next. And before we exit this slide, the last thing I want to mention is that, yes, if you're thinking about this number and it looks kind of suspicious, you're right. This is a measurement. And so how many sig figs does this number have? In fact, scientists have studied Avogadro's number. They've done experiments to prove how many particles are in a balloon and so forth. And there's actually quite a few more decimal places beyond this. However, in this class, we're only going to need to learn Avogadro's number to 4 places, and that's good enough for all of the calculations we'll do in this class. So if you look at, say, Wikipedia or something, it does go on for more digits. We're just going to go to 4. Oh, a good question. So how accurately can scientists count one particle? Well, as you could see in a few slides ago, we've gone to the point where we can image a single particle. So we can count how many particles are in say a sample. One of the first ways that scientists actually confirmed Avogadro's number. For hundreds of years, it was suspected that this was right, and it was consistent with what we would do in experiments, but no one was able to prove it by actually counting atoms until the 20th century. And the first way they did that was actually through a technique called X-ray diffraction. And so X-ray diffraction means that we take a sample, and in most cases, when you do this, it's a solid, crystalline solid, and we should know that word by now, right? From the pre-lecture. So a crystalline solid, say like a grain of salt, and what you do is you blast it with X-rays, the same kind of X-rays you might, take in the dentist's office or something. But what happens is that the atoms themselves, much like you're seeing here, the atoms will actually bend the X-rays as they pass through. So much like you take a prism and the light bends, the same thing happens when you shine X-rays through a grain of salt. Now, how does this help us? On the other side of the detector, there's a sort of photographic film that's going to display the X-ray. So when the X-ray hits the film, it makes an image, like a literal X-ray for your bones. But what happens is that you see a bunch of stripe and dot patterns. And from geometry, looking at the angles that these X-rays have sort of been deflected, you can actually figure out the geometry and how many sort of work out what the shape of a grain of salt is, and therefore how many atoms there are. And then by doing a little bit more math, you can figure out Avogadro's number. Oh, and so to return to Avogadro's number, hopefully that was a satisfying story. I think it's really cool. I get excited for that. So this would not be considered an exact number. So remember, we have 3 different types of exact numbers. We have, and this might be a good place to sort of just review that. So this is not part of this topic, it's an aside. But remember, we have exact numbers, and those have the infinite sig figs. Among those exact numbers, what do we have? We have counting numbers. And I want to stress that Avogadro's number doesn't count as a counting number. When we say a counting number, we mean something that we actually, with our eyes, counted. So when I say that there are 2 cats in this office, I literally counted. So that's infinite precision, infinite sig figs, because there is no estimation there. There is no rounding there. I can see a cat there, and I can see a cat there. By the way, I have a couple cats. So Avogadro's number is not a counting number. It was actually calculated from experiments, so it does have sig figs. When we say counting number, we mean literally something that'll go 1, 2, 3. Okay, there are exactly 3 there. So it's not a counting number. And just for the sake of completeness, what are the other exact numbers? Formula numbers. And that's an example being the diameter of a circle is 2 times its radius. This 2 is part of the formula for the diameter. And so it's not from a measurement, it's from the definition of what a diameter radius relationship is. And then the final one, well, what is the final one? Let's see, we have counting, we have formula, and we have definition. And that's when it's something that doesn't come from nature, but something that our society has sort of decided this is true. And an example of a definition would be things like there are 12 inches in 1 foot, right? It's not a law of nature, but it is something that we as a society said, we are being precise here. We will call 12 inches exactly 1 foot by the definition. And so all 3 of these, remember, they have to fit this precise set of definitions. So all 3 of these are an example of exact. And we say that exact has the infinite sig figs. So, and then just to be clear again, I just want to emphasize that it doesn't mean that a single example has to check all 3 boxes at the same time. As long as it checks one of these boxes, it's considered an exact number. So a counting number is not the same as a formula number, but both of them are considered exact numbers with infinite sig figs. All right. I'm glad we get this opportunity to sort of discuss that. So it is measured. Awesome. So here I have a few practice just to use Avogadro's number in sort of different ways, and just practice the idea that even though it's brand new, we still utilize the same type of math technique that we've been doing so far. And that's going to be the conversion factor canceling method. So we can ask how many water molecules are in 2.0 times 10 to the minus 8 moles of water. And this is an example of the grains of sand versus moles of sand issue. Notice how just the English language makes it a little bit weird. Because what are the individual things that we're counting in this practice A? We're counting water molecules, right? So that can be a little bit jarring because the other unit is actually moles of water. So notice that they're not exactly identical to each other, but if we take a moment to reflect on what they're talking about, it's the same thing as saying how much sand is on the beach. Well, we have 1,000 grains of sand. Notice the word grain doesn't come up in, in my first part of that statement, but to make it sort of grammatically correct, it has to. And that's the weird thing about the moles, because it's the same thing happening here. The unit is water molecules on one side and then moles of water, which do not exactly look identical to each other. But if we take a moment to reflect, it should make sense that what we're talking about are water molecules are the tiny particles, and a mole of water is a group of those particles. And how much is in that group? 6.022 times 10 to the 23 of them. So because they're so small, I can't count them directly, so we use a conversion factor to do it instead. But that just means that my given is moles of water. Again, for abbreviation purposes, we tend to drop the E. Doesn't really shorten it by that much, but that is how we abbreviate mole. And we desire water molecules. Notice I have to be very careful and spell things correctly, because if I try to abbreviate molecule, it might get confusing. Notice that both words start with the first 3 letters, and oftentimes students flip them around and switch them, because I admit it is a little confusing, the fact that both words start with the first 3 letters, the same first 3 letters. So we have to be a little bit careful here. So let's do it. Let's convert this number to the new unit. So how's that going to look? I'm going to start with the number I want to convert, 10 to the minus 8, and it's moles of water. And I'm going to put the conversion factor down. So again, as we're learning, a great starting point is to think about, well, how do I get 2 of these to cancel each other? It means that my first unit has to be in the bottom of this fraction. So that's going to be, and I'm already anticipating that I've not given myself enough space. So I'm going to erase this a little bit because I have a feeling I'm going to run out of room. So moles of water, because they need to match for the cancellation. And so what does that mean? Well, to go back one, a mole of things, the other unit is the actual individual things. So when I talk about a mole of water, it means I'm counting water molecules. So that means I'm going to have water molecules. How many? 6.022 times 10 to the 23 water molecules. And I knew it. I knew that I was going to run out of room. So good thing I anticipated that. That's going to get our units to cancel in the way that we want. Now, the other thing I want to mention is the biggest issue that I see at this point. Students tend to be very good at figuring out which unit goes on the bottom and which unit goes on the top, but not so strong at where do I put each number. This is why I emphasize that we should be thinking of the mole and Avogadro's number as the chemist's dozen. If it's at all confusing where you put the number, think of it like the dozen. I have 12 eggs in a dozen eggs. So the 1 goes with the dozen and the 12 goes with the thing you're counting. And in the same way, if I have a mole of things and I have this number, we want to go with, well, a mole is a chemist's dozen. So I should think of it in the same way. 1 mole of things is equal to 6.022 times 10 to the 23 things. And so that's how I know if mole is down here, that gets the invisible 1. And then the number itself, Avogadro's number, goes with the thing that I'm counting. And that's where we'll get the cancellation. And we should get this answer. If at any point my writing is hard to read, just let me know. It takes a lot of effort for me to write clearly, so I might sort of slip into bad habits of chicken scratch, right? Hard to read writing. Okay, the second one, I'm sure some of you have probably already put it together, but let's do it. How many moles of water is 3.0 times 10 to the 6 water molecules? So again, we look for the question and what it's asking for. So it's how many moles versus, now this is the number I'm given with water molecules. So that's how I'm going to set it up. I'm going to start with the number I want to convert, times 10 to the 6 water, I'll just put it like this, molecules. And now I'm going to put a conversion factor. Okay, so let's practice. What's going to go where? So water molecules has to go on the bottom so that they cancel. By process of elimination, that means moles of water goes on the top. So again, a mole is a chemist's dozen. So 1 dozen things, pick an item, 1 dozen pennies is 12 pennies. A chemist's dozen of pennies will be 6.022. So that means the 1 goes with the grouping, 1 mole, 1 dozen. And 6.022 times 10 to the 23 goes on the other side. This will give us our cancellation and leaves us with the unit that we want. So just a sneaky opportunity to practice conversions one more time with a new one. No, you won't have to memorize this conversion by 1 p.m. today. So don't worry about that. just the prefix stuff and the sig fig stuff and all that good stuff. But you will have to memorize it eventually. Okay, pausing another moment for a question, if any. Oh, actually, as you're thinking about your question, I'm going to pause for a moment. I forgot my glass of water, so I'm going to go grab my glass of water. If you want to type a question or clarify something, please do so, but I will be right back. Okay, thank you for your patience. I have my water now. Yeah. And just a reminder, yeah, POGLs are due in the beginning. Those are the only things where their kind of time is different. Oh, are the conversions? Oh, asking another question came up asking about the quiz and conversions. So again, only the conversions that are listed in that module for the quiz that mentioned things like, yes, prefixes, yes, some of the ones that were in the table, but if it was a conversion that I said you don't have to memorize, then no, you don't have to memorize it. But prefixes, whether you like it or not, you'll have to, because more and more math in this course will involve them. And I get students who say, how can I possibly memorize all of these? It's after you've done it 100 times, you will definitely know it. So yes, we do memorize the prefixes. Excuse me. Okay, hopefully I've satisfactorily answered those questions. The rest of the lecture is going to focus on the qualitative observations, those classifying matter. And so we already have in our back pocket the idea of phases, right? Solid, liquid, gas, and what they're doing. The second way we classify matter is by composition, or in other words, what it's made of. So that's, you know, the informal way to describe what composition is. So there are 4 categories. So there's 2 categories broken into another 2 categories. First, we have the pure substances versus the mixtures. Pure substances are made of one type of particle. So it's a lot of the same particle over and over. Whereas mixtures are made of more than one type of particle. So that's the first way we classify matter, is by its particles, and are they all the same, or is there literally, you use the word mix. So are they mixed with many? So among those, we have, among the pure substances, we have elements and compounds. And among the mixtures, we have homogeneous mixtures and heterogeneous or heterogeneous mixtures. Let's go into more detail on how are these categories different from each other, and when is it appropriate to identify something as one of these categories. So starting with the first one. Pure substances. Of our pure substances, we can have elements. So first, just a reminder, a pure substance is made of only one type of particle. It can be a repeating identical atom or repeating identical molecules. So an element is a substance that cannot be broken down into simpler substances. These substances contain only one type of atom. You might already be familiar with the periodic table of the elements. If you're not, that's okay. We will be talking about the periodic table next week, and you will be memorizing the periodic table next week. In fact, if you want to do it early, that might not be a bad idea. I should maybe put in a teaser for that right now, but you will be expected to be able to identify where the elements are on the table. So what that means is that if I ask you for an element, you know where to look for it. To do this, you'll need to memorize, and flashcards are a great way to do this, the name of the element, and then it has a 1 or 2 letter symbol that comes up on the table. So that's what you really need to memorize. The name of the element, and then what is its symbol. In many cases, it's nice. It's usually like the first letter of the name, but some cases it's not nice. That's why flashcards are good. So if the substance is on the periodic table, then it is an element. It is what I like to call it is the alphabet of the universe. These are all of the little letters that make all of the words of matter. So, you know, everything can be broken down into the letters of our chemical alphabet. And so that's what we're going to focus on when we talk about elements. Elements can exist in many different forms, what we call allotropes. So allotropes are, can be 2 different forms of the same element. It might be 3 sometimes. It just means multiple. So example would be graphite, which is the stuff in your pencil lead, and diamond. They are actually both made of pure carbon atoms. So we say that they are allotropes of carbon. So an allotrope is just 2 different versions of the same element. So carbon is an element, and the 2 ways we see it in nature are through graphite and diamond. Here are some examples of elemental matter in sort of a pictorial or rather cartoon kind of form. So remember, a circle represents an atom. So elements can be monatomic, meaning 1 atom. And we see here that this is a pure element because it's all made of this dark colored atom. So this is monatomic because each separate particle is a single atom. Just a reminder, all of the lecture slides are always in the synchronous lecture page. This is module 3. You just have to keep up with which module we're on. So we're on 3 right now. If it's diatomic, it means that the element is made out of a molecule that consists of 2 atoms put together. So we would write that as a Y2 for this sort of, we've labeled it Y. So if these are element Y, then the diatomic element will be Y2. It's telling us each particle is 2 put together. And then triatomic, and you can probably see the pattern already, triatomic means 3. So each particle is 3. So these are all examples of elemental matter. One thing to be aware of, and something that will be very important the further we go in this course, is that we need to memorize the 7 diatomic elements, or we call them the diatomic 7. So 7 elemental substances exist on Earth as diatomics. So in other words, it's double. Each particle is 2 atoms of that element. So they exist as diatomics on at room temperature. And yeah, we can use the terms monatomic, diatomic, and so forth for anything to label. So if it's made out, if each particle is made out of 3, then it's triatomic. So yeah, H2O is triatomic because it has 3 total atoms in it. Where are these located on the periodic table? What's nice is that these elements that we call the diatomic 7 actually kind of make the number 7 for the most part. So they start with N for nitrogen, and they kind of go and make the 7 shape. The only one that doesn't exist in this sort of geometry is hydrogen. Hydrogen is a sneaky one. It's actually the first element, and it's way on the other end. But that's the way I like to emphasize it. The diatomic 7 they make a little 7 on the periodic table, and then hydrogen's just a little bit tricky. Some students like this mnemonic to help them memorize which elements are diatomic. Have no fear of ice cold beer. So each letter is part of the way you memorize the different elements. So hydrogen, nitrogen, you notice fluorine, fear, O for oxygen, iodine, chlorine, bromine. So those are what those symbols mean. And it means that if I had a beaker of bromine, for example, the particles inside the bromine look like what you see in the cartoon. They're 2 bromines together. What you'll need to memorize is that these are the element names. This is how we would write it. So hydrogen is H, but it exists in nature as H2. And then you'll need to know that it would look like something like this picture. So that's kind of our first stop with the elements. Of course, we're going to add a lot more to that description and that discussion, but that's the first thing. Which of our elements? Well, first of all, what are the elements? There are all of those named substances on the table. Which ones are diatomic? And we use have no fear of ice cold beer as our way to remember. In addition to elements, we can have compounds. So again, elements and compounds are both considered pure substances because they're only made of one type of particle. Only this time, when we have a compound, it's a substance whose particles are made of 2 or more elements in fixed proportions. Meaning, much like a recipe, it's 1 part hydrogen, right? 1 part oxygen or something like that. So a compound is different because not all of the dots are the same. And so, for example, water is a compound because it's triatomic, 3 atoms put together. So we would call this a triatomic molecule. And 2 of the atoms are the same, but 1 is different. So a compound is when not all of the atoms are the same. So just to reiterate, the diatomic 7 are elements because each of their particles is the same. It's H and H, or N and N, or O and O, and so forth. But water is a compound because 1 out of the 3 is not like the others, right? So other examples are table salt. It's actually made of 2 elements, sodium and chlorine, and sort of has a nice, so by the way, what would we call this type of substance in terms of our phase terminology? If I see this picture, I should be thinking
solid.
Solid and
crystalline.
And crystalline, yeah. So again, crystalline means a nice ordered repeating pattern. We should be able to pick it out by a picture. Okay, so that's a crystalline solid. And then one of the key differences between compounds and elements is the fact that, well, elements are already the letters of the alphabet. We can't break them into any new letters, but compounds are made of elements put together. So compounds can be decomposed, or in other words, we can turn them back into their elements. So it's much like you pull all of the letters of a word apart. A compound can have its atoms converted back into their elements. And this is an example of that. This, at one point in time, not anymore, but this is sugar. This is table sugar. But table sugar is actually made out of 3 elements. It's made out of carbon, hydrogen, and oxygen. And so what you're seeing here is the sugar is actually turning back into one of the elements, and that's what this solid sort of mass is here. Any guesses which element this one is?
Carbon?
Yeah, it's the carbon, and it kind of reminds you of like the lead in your pencil too, right? Or if you've ever actually had experience, there a lot of products these days have activated carbon, activated, whatever. It's black, right? So this is turning back into carbon. So what's actually happening, and we'll talk about, chemical reactions later, is that this beaker of sugar was combined with sulfuric acid. And what the sulfuric acid is doing is it's literally ripping off the hydrogen and oxygen atoms from the sugar and turning them back into water. And it's hard to see in this image, but this sort of mass of carbon is steaming. It's because all the water is being dehydrated from the sugar. So it's losing all of this water in terms of steam, and we're getting back to elemental carbon. So that's a key difference between a compound and an element. Compounds can decompose back to their elements. Elements are kind of the bottom floor. There's nowhere lower you can go than an element. So that's our first category of the pure substances, compounds and elements. Our second are mixtures. So a mixture is a combination of two or more pure substances. So two or more non-identical types of particles are present in the overall object. When we mix pure substances, we can tell the particles apart because they are not bonded together or connected together. So if I give you a cartoon version, I can see this is a mixture because I have two different types of atoms here. I have literally mixed them together. And the same thing goes, these are molecules. And I can tell there are different kinds mixed together here. And then the same thing goes with this. A mixture is categorized by how uniform its composition is. So another way to think of that is sort of, is it thoroughly mixed on an atomic level, or is it not thoroughly mixed on an atomic level? And that means we have two different classifications for that condition. So the first is homogeneous, and you might have heard that word before. I can think of a few examples where you might hear it in everyday. But homogeneous mixtures are such that the composition of the mixture is uniform throughout the substance, meaning thoroughly mixed, all of the same. An example of that would be a liquid solution. So we're going to talk at length about solutions later. A solution is a homogeneous liquid. Maybe I'll emphasize liquid phase mixture. So that's literally what a solution is. It's a homogeneous liquid solution, liquid mixture. So like you might hear the phrases saltwater solution, sugar solution. It means a thoroughly mixed liquid made, in that case, salt mixed with water. These are an example of a different kind of salt. These are nickel salts. And actually, depending on the composition, what exactly is present here, they actually come out in nice different colors. So that's pretty cool. But why is this considered homogeneous? It's because the composition does not vary depending on the position you're looking at in the solution. So if I sort of look at all of the particles throughout this, say, sort of light green solution, no matter where I look, the top, the bottom, the left, the right, there's roughly equal proportions of, or roughly the same proportions of the different particles, right? We might have water molecules mixed with nickel atoms and so forth. If it's homogeneous, it means that on an atomic level, it looks pretty thoroughly mixed. The opposite is heterogeneous mixtures. These are not uniform throughout, so not thoroughly mixed. The key idea is that if a substance is such that you can see the components of the mixture with your eyes, then it's definitely heterogeneous. So for example, ice cream sundaes. If we're considering the ice cream sundaes as one whole substance, then that means this would be considered a heterogeneous or heterogeneous mixture. So in this case, I notice that I can tell the toppings from the ice cream. If I take a bite, and for this example where we can taste it, if we take a bite of this from the top, it's going to taste like pecans, right? If we take a bite from the bottom, it's going to taste like pure vanilla ice cream. And if we take a bite from the middle, it's going to be like chocolate syrup. So again, it's because the composition is not thoroughly mixed. It's not the same everywhere. And as long as that happens, we would consider it heterogeneous. So take the salt water idea. Sometimes if we dump too much salt into, like way too much, there might be some salt crystals that don't dissolve anymore. So at that point, it's not the same throughout. If you're, maybe a better example would be sugar water. If I have crystals of sugar at the bottom that didn't dissolve, then it becomes heterogeneous. Because if I take a sip from the top, it's nice and pleasant maybe, but if I take a sip from the bottom with a straw, I'm gonna have huge chunks of sugar in my mouth and it's not gonna be as pleasant. So anytime that we can tell one position has a different amount of substance than the other, for example, like an ice cream sundae, that's heterogeneous. Another example would be if we have some kind of substance that doesn't dissolve in water. So this is actually a different kind of salt, not like table salt. It's called manganese 2 hydroxide, and this is its chemical formula, which we'll talk about later. But we see that we add it to water and it doesn't dissolve. Portions of solid are found at the bottom, and some are even floating at the top. And there's sort of water interspersed. Anytime we have a situation like this, that is going to be a heterogeneous mixture. Here's and we're getting some good examples. Yeah, so if I pour oil into water, what do I get? So I pour oil and water together. You're going to get a single substance. It's liquid in the cup, perhaps, but the liquid at the top is going to be pure oil. The liquid at the bottom is going to be pure water for the most part. So even though the substance in my cup is a liquid, it is not a pure liquid, it is a mixture. And because I can see the two layers, it is a heterogeneous mixture. So that's another good example, oil and water. They don't mix together. I can see the parts. So that would be an example of a heterogeneous mixture. On some level, these are they're meant to make our discussions of matter as helpful as possible. So sometimes it might seem like the distinction between, say, especially heterogeneous and homogeneous, it's kind of arbitrary. It's kind of weird. It's like, well, I might not see it that way. The idea is that if we can all get on the same page and be consistent, it makes whenever I discuss something with you a lot clearer. So for some of these, you might feel a little bit frustrated. I understand. It's like, well, does that really count as heterogeneous and so forth? This is why we practice. And I really emphasize, if you can see the bits with your eyes, then it would be heterogeneous. And probably to give you an example that might throw you off is, how would you classify a glass of ice water? So a nice refreshing glass of ice water. Which term would I use? this is we're getting kind of nervous, right? And this is where it gets kind of frustrating, because a lot of people would actually argue that it's a heterogeneous mixture. And that's frustrating, right? The reason being is that even though it's the same compound, I love that we're using the word compound, even though it's the same compound, they're in different phases of matter, so they can be, we can tell them apart. And so when two of the same phase are present together, it's and thoroughly mixed, it's homogeneous. But if it's the same substance but in two different phases, we can tell those phases apart. People tend to label that as heterogeneous because you can see. And the reason why you might be frustrated, it's like, well, isn't it the same thing? And yeah, it is the same thing, and they're both identical compounds. But one example of why it might matter to actually classify it as such is that take the properties of ice versus the properties of liquid water. For example, the density. So with that in mind, it does make it a fuller, more complete conversation to us to say, look, it's water in here, but we need to be clear that they're in different phases, and some of their properties actually end up being different, like density, like ice can float on water. So in that sense, it is important to sort of be nitpicky. I know that that might be what it is, where it feels very nitpicky, but that's what we have to sort of go with so that we make sure we understand. And yeah, presumably they have different amounts of energy. In fact, the end of this, we'll talk about where do we get ice water? Like where does that, how can chemists create a container that has ice and water simultaneously that won't melt? So that's the thing. And it has to do with energy. Oh, and so those are the oh, and then we have an example, cup of sand. If it's, well, it depends. If it's all the same grain, all the same kind of sand, then that might be considered if it's all the same compound, it might be just considered a compound. I think you might be referring to, what if you have like little specks of like there's like black sand and white sand and a little bit of shells. If it's like from the beach, then that would be a heterogeneous mixture, because you have different kinds of sand grains there, and you can probably see them with your eyes. Okay, whew, there's a lot of labeling. So let's try it one more time with a picture. So this is a typical chemical representation at the particulate level of the main components of pure air. So my question to you is to brainstorm and think about how many different substances are in this representation. So how many different substances? How many different elemental substances are there? And how many different compounds are there? So we're talking about everything within the black box. We want to say how many substances total, how many elemental, and how many different compounds. So we could try maybe circling them. So here is the particle of one substance. Here's a different, so that's 2. A different, so that's 3, 4, and here's one more, 5. So there are 5 total substances based on 5 particles. Each particle is a speck of a different substance. How many different elemental substances are there? So let's use a different color. So what's the definition of elemental? Same type of atom in particle. So this would be elemental because its particle has the same blue in total. This is also elemental because it's the same. And then this one by default, right? By sort of like it has to be because there's only one atom there. That's a substance. So this is going to be 3. And that means this guy and this guy are compounds. They're made of different elements. So that's 2. So there you go. 5 types of substances. 3 of them are elemental. 2 of them are compounds. Do we have any of the diatomic 7 in here? Does air contain any of the diatomic 7? Yeah, we should be able to identify it just from the picture, right? The blue is 2 identical atoms, diatomic. The red is also. In fact, what this is depicting, the blue is for nitrogen. Remember, have no fear. And the red is for oxygen. So yes, we do see 2 members of the diatomic 7 here. And that's basically what I expect of you from this part, being able to clarify or classify, I should say, substances based off of a description, or from a picture like this one, be able to describe, is it a compound? Is it an element? Is it a mixture? And also one thing that's not asked, but we might ask it here. This is a kind of silly for this example, but what phase of matter would you expect this to represent? And I think it's something we all know because we already mentioned it's air, that it's a gas. But what is the giveaway that it's a gas? The spacing, yeah, they're far apart from each other, as well as, or maybe you're trying, maybe some of you are mentioning it through staying spacing, but the other thing I'm looking for is occupying all of the volume of the container. A liquid would only be at the bottom, right? And it's pretty close together. Solid would be pretty sort of even closer, as well as probably have a specific shape, right? Liquids would ooze to fill the bottom of the container, but a solid, if it's like a rock, I mean, it's not going to fill out any of its container. But a gas, that's what I want to see you look for. It's filling the total volume of its container. So not only is it down here, but it's way up here, and that's something specific to gases. But yeah. Oh, there's a good question, but it's kind of like, hey, professor, couldn't you trick us by like filling the whole box with liquid, and then technically the liquid is all the way at the top, and yet it kind of looks like it would be filling its space? I'm not going to trick you like that. So there's going to be no trick questions where it's like, there's ambiguity, right? So, but that's a good point. If I filled this box with liquid, all of the particles would go to the top, but it's kind of, that's kind of a mean trick, and I'm not going to do that. Okay, so the reason why we want to identify substances is to collect more information about them. And one of the things that we can do is identify the properties. Remember, we used that word, and we actually focused on a physical property in our last lecture with density, but that's an example of a property that we can observe in matter. So that's the next stop. We have physical properties. These are properties that of a substance that does not require the substance to change its identity. What does that mean? So when I say it doesn't require a change of identity, what we're saying is that in order to demonstrate this property, its particles are not harmed in any way, meaning that if it were triatomic, it remains triatomic, and it has 2 white atoms and 1 red atom, it remains that way. So when what I'd like to do is emphasize that. So this is particles identical before and after. So something like we can test the melting point or the melting temperature of ice by letting the ice melt, right? But prior to testing this, the ice is made out of water molecules. The liquid water that we get at the end, they're still water molecules. So the particles of the substance were not harmed in any way by this change. So that's indicative of melting is physical. Contrast that with chemical. A chemical property is a property of a substance that is displayed by changing its composition. So for example, if I burn a cotton ball, it turns to ash. We see smoke. We see sort of vapors coming off, gas coming off. So we see that that substance changed in an important way. That in fact, several different substances with very different appearances are now present after I burn, say in this case, in this picture, it's a cotton ball. It might be helpful to go through a few examples. So, and I mentioned that the way we test physical properties are through changes. So that's exactly our next terminology. Substances display physical and chemical properties through physical and chemical changes. So what is that? A chemical change is the conversion of a substance to a new substance via a chemical reaction. And when we say new substance, we mean the particle composition has changed. And as an example here, this is actually an image of baking soda added to vinegar. So we might recognize that it bubbles. Why does it bubble? It's because a chemical change is proceeding. And so to visualize it, so we're focusing right now with particles, but eventually we're going to use terminology of chemical equations and reactants and products. What this means is that reactants represent the particles before the change, and products represent the particles after the change. And so what we see is that, well, baking soda and vinegar have very distinct composition. This is actually a simplified version of what's going on, not to make it too cluttered. But what we see is that when these particles come together, they turn into new particles with new combinations of their atoms. So whenever this happens, whenever the before picture is different from the after picture, like so, then we've gone through a chemical change. And so we would say that baking soda and vinegar being added together will undergo a chemical change. The same thing goes with the cotton ball, right? It's because the chemical structure, right, how many atoms there are in the particles of cotton reorganizes, changes, right? The smoke coming off includes carbon dioxide. So we're making new types of particles. Whenever this happens, we have a chemical change. Contrast that to physical changes where the appearance changes, but the particles are the same as they were before. So some examples are phase changes. So turning something from a solid to a liquid or a liquid to a gas. Those are considered physical physical changes. Shattering, tearing, or cutting. Anytime you're changing the appearance in some way, that is going to be a physical change. So even though I shatter glass, the pieces are still glass. And so that's the big difference between a chemical change and a physical change. When I add baking soda and vinegar together, the bubbles coming off are neither baking soda nor vinegar. So they're different. So that's chemical. But if I put a tea kettle on the stove filled with water and I see the steam coming off, well, the steam is made out of water molecules, just like it was before when it was liquid. So boiling water is an example of a physical change. So this is all so that we can first identify and distinguish matter. We want to have conversations. So we want to know, what are the properties? Does this have chemical properties that we're focusing on, or physical properties? And to be able to understand what that means. And it's all about building up this conversation that we're going to keep having with matter. To do that, we need to build on our vocabulary of when I see something, I should be able to explain it appropriately to someone else. So what is a big application of this? So why do we care about, say, composition and phases? One way to do it is, one way to sort of apply this is through being able to separate substances from each other. So remember, we're focusing on these bigger picture questions, but as sort of a major bullet point in why we're doing this, yeah, we want to distinguish, differentiate, so tell things apart and identify. But one way we use this information is through separation. So the appropriate way, the appropriate way that we apply separations in chemistry is to focus on a major difference in a physical property. So in other words, something that's very different between the two things that I want to separate. This allows us to separate mixtures. And one sort of vocab word that we use this for, we say we purify one substance from the other. You know, like you want to purify a medication as you know, if you're a part of a drug company, you want to be able to purify the drug from all of the possible side products, ingredients, and so forth. So why do we focus on physical properties and physical separations? Well, remember what we learned about the word physical change and physical property. Substances are separated by a physical property, means that the composition of neither is changed during the procedure. In other words, we're pulling them apart without harming them. So if I have it sort of visually, we're trying to get them into separate sort of locations, but keeping them intact. And that's why we focus on physical changes in order to separate substances instead of chemical changes, because we might destroy an important substance in the process. And that's not what we want to do. Sometimes it is. But if we want to separate both of them and keep them intact, we focus on physical properties. One example that we have is filtration. So we usually have a mixture in here. This mixture typically contains a liquid. In the case of filtration, that's the most common way we do it. But it has two very distinct physical properties. One is a liquid and one remains as a solid. So you've probably done this if you've ever brewed coffee in a coffee maker, right? Your coffee grounds are large solid particles, and you're passing liquid water through them. And so it requires a funnel and a funnel paper to be the barrier. But what we're going to do is the paper is able to distinguish two different kinds of particles based off of size. Large solid particles are going to be are not going to be able to pass through, but water molecules are small enough to go right through the paper. So our physical property that we're exploiting here is particle size. Some particles are too big to go through, while some particles can go through. So in this case, liquid particles are going to be able to pass, but the solid particles are going to remain. So using our 4 classifications of matter, what kind of substances work best with filtration? Is it going to be homogeneous mixtures or heterogeneous mixtures? Filtration works best with
Heterogeneous?
well, heterogeneous might be a good idea because heterogeneous are in which the composition is not uniform. Because if we have solid and liquid together in a beaker, so okay, that's pretty, that's supposed to be a beaker with water and like, something sand or something chunky on the bottom. Of something heterogeneous like a solid liquid heterogeneous mixture will be a good candidate for filtration because by fact that the solid isn't dissolving and is remaining sort of large enough pieces for me to see with my eye, it must mean that that the size of the particles is going to be large and they are going to be prevented from going through the filter paper. So exactly, so we use filtration to exploit a physical property, physical size of biparticles, as well as solubility. So things that don't dissolve usually remain large chunks, so that we can do interesting things. So that's one example of why we want to look at the composition of matter. The other would be to sort of explore the properties of the different phases. So at this point, I'd like to focus the remainder of our time on the phases of matter. And so unfortunately, the simulation doesn't work on here. So I'm going to have to do some swapping to another screen to get it to work. So bear with me for 1 second. Oh no. It's not showing up. Ah. Okay. I wonder why. One last try. Oh, sorry. I'm mumbling to myself because I'm trying to figure out how to make this work. Oh man. That's very odd that it's not working today because it was working before. Yeah. That's weird. Okay. So what I'm going to have to do is I'm going to have to troubleshoot this myself on my own time and get it, maybe record it in a different way. Okay. So we're going to have to skip that. So what I'll do is I'll just continue and I'll see if I can record it on my own. It was a really nice recording. Let's do, screen share. Okay. What I was going to do next is focus on the phases of matter, but from a different perspective. What you were going to see was a box that had sort of these particles in it. And they're all moving. So I'm going to do a little arrow to show that they're moving. So they're all moving and so forth. And what was nice about the simulation is that it allowed us to, using a slide bar, it allowed us to control the temperature as well as the size of the box that these particles can roam. And what you may already know, perhaps this is something you've seen in another class, is that when you change the temperature of the particles, you change how they move. And specifically, you're changing how fast they collide with one another and sort of how far they can sort of range throughout the box. So what we say is that temperature is proportional to the kinetic energy of the particles. This means, kinetic means movement. So the movement energy, the energy that's used by particles to move. So what we would find is that in a cold container, the particles are really close together. And in fact, they're so close together, they don't really have a lot of room to move. But when the particles are put into a hot container, let me say hot, they have lots of room to move. So what we should have been able to recognize, and maybe my drawing is enough to sort of get that image across, is that in the cold scenario, the particles don't have a lot of energy to move, and so they move very slowly. And in fact, one thing that we emphasize is that all particles have some, it depends on the particles, but some attractions to each other. So when we make a substance cold, the particles move slower, and if they're very sticky or attracted to each other, they might cling to one another. And so this suggests that when we make objects really cold, they tend to be close together because they're stuck and they move very slowly. And so what kind of phase of matter does it sound like we have in the case when we make an object really cold? So we're talking about the solids, the liquids, the gases. If it's really cold, and yeah, they're solid, right? Whereas when we're a gas, there's enough energy to move really fast and unstick yourself, so you spread out. So we see the transition that if I change the temperature, a cold object might start off solid, but as I warm it, it might turn to liquid, and then further energy will turn it into gas. And so that's sort of the big idea from the simulation. The other thing that that we see in the simulation is how the size of the box affects the particles. And so we might expect in a scenario where the temperature is really high, that my particles are really far apart. But if all of a sudden I make the box really tiny, even though the box is, even though these particles want to be far apart, we physically make them close together. So there are actually two ways that we can turn one phase of matter into another. We can change the temperature, which makes them move at a different speed, or we can change what we call the pressure. It's the push down on this substance. And we say it's proportional to the collisions of the particles. The more times that my particles cling to one another, hit into one another, the more likely they are going to stick. So if I shrink the container that they're in, I can make a gas and compressed enough that it might turn back into, say, a liquid where it's not as, or maybe they're closer together particles, or I can turn it all the way to solid where the particles are very close to each other. So there are two sort of issues, and they're independent of one another. So I can change the pressure without having to change the temperature and the kinetic energy. So there are two distinct ways to turn one phase of matter into another. I can either heat up or cool down my substance to turn it into one phase of matter or another, or I can actually push on my substance, cram it down so that it turns into a different phase of matter. In fact, that's a popular way to turn gases back into liquids, like how we need high pressure propane tanks to get liquid propane for, say, fuel purposes. That's literally what we're doing. We're turning it into a liquid by cramming the particles together until they turn back into that phase of matter. So the less room I give my particles, the more pressure is on them, the more they want to stick together. And we know those phases of matter are more like liquids and solids. But if we give them a lot of room to move, it means that when they start to sort of move apart from each other, they might sort of float away in a sense. And so we might get gases in that way. So pressure is one technique that you might not have thought about to change a liquid to a gas or a gas to a liquid, but it's how it's done when sort of making propane or putting propane into tanks. So we should be able to, hopefully from my description, we should be able to answer this question. Thinking about the movement of particles in each of the phases, we expect particles to behave like a gas when, and I have options. So do we expect gases to be favorable in high temperature or low temperature, high pressure or low pressure? Again, thinking about what makes a gas happy, gases are really far apart.
High temperature and low pressure.
So yeah, exactly. High temperature, low pressure. So we expect substances to behave like gases under high temperature and low pressure conditions. And solids would be the opposite, right? Cool them down so their particles can't break free and really cram them so they don't take up a lot of space. So we can do this kind of analysis to figure out what's the best way to go from one phase to the next. So say if we wanted to turn a liquid to a gas, what should we do to the pressure and the temperature? So it's a liquid right now. We want to turn it into a gas. Well, we would want to do some combination of heating it, high temperature, and low pressure. Oh yeah, and we have a good observation. The idea of maybe filling a ball with air from an air pump. As you pump more air, it becomes harder to push it in. It's because of the particles having less room to move around. If they have less room, they're actually hitting into each other more. They're bumping in, colliding. And so they're trying to sort of push each other away. And so that it becomes harder. We're building up pressure because more particles means more collisions that we're seeing. So pressure is something that we're going to talk in great detail at the end of the week, but a few notes on it. What we call pressure is the push that we feel of the air around us. There are air molecules everywhere, and they're constantly hitting into us. And that push is what we feel on our bodies, or sometimes we don't even notice it. We call this atmospheric pressure. Standard, what we consider normal or standard, is called atmospheric pressure, and it's basically the pressure you feel at sea level, and it's called it's given the unit of atmosphere, and so we say normal pressure is 1 atmosphere, and so if we have a number greater than 1, it means we have higher pressure than normal air, and if it's lower than 1, it means we have pressure that is lower than normal. Older units are also common. We have atmospheres, but we also have millimeters of mercury, and that's actually the symbol for it. MM is for millimeter and HG is for mercury, also called the torr. So when we talk about air pressure, we're talking about the same thing that we're discussing with the sort of particles. It's this push as they're being sort of bombarding everything around us. And so that's what we consider air pressure. But we'll focus on how pressure and temperature make the phases in what we call a phase diagram, or a map, I like to think of it, of the phases. It's broken into 3 segments that you see here. So we have the solid area, the liquid area, the gas area. All phase diagrams of pure substances look like this. The only difference will be maybe the angle that these lines are intersecting at. But it's always going to be a Y shape that looks like this. The solid is up at the top, the liquid is near the middle, and gas is at the end near the bottom. Now, hopefully, the labels make sense to us intuitively. So let's take a moment to sort of get our bearings with this diagram. We see that the x-axis is temperature, the y-axis is pressure. So that means as I go right along the graph, my temperature is going up. As I'm going up on the graph, my pressure is going up. And remember, pressure is like we're cramming the substance into a tighter space. We're pushing down on it. Either we're pushing it by pumping maybe air into the container, making all of the particles cram together, or we're doing it some other way, like with a piston actually pushing physically onto the substance. But as we're going up the graph, we're going up in pressure. So notice that this actually corresponds to the exact conclusions that we made in the previous slides about solid favors this, gas favors that. If I take a look at this region, what are my coordinates? Well, if I take a look at sort of the relative position, when I'm here on the left-hand side of the x-axis, the temperature axis, it means I'm cold temperature, right? Versus hot temperature. So solids are found up at the top. They are at the position with cold temperatures, sort of left-hand side of the X, and sure enough, high pressures. So solids favor low temperature, high pressure. Gases, they tend to be higher temperature, and they're at near the bottom of the y-axis, low pressure. That's exactly what we thought they were. And liquids are in the middle, because they're kind of, you might argue, they're kind of like in the middle of being gas or solid. So if I decide to sort of put a point on my graph, I might argue, or I might be able to determine what the phase of that substance is. So as an example, if I were here on my phase diagram, I can use the coordinates to tell me what temperature and what pressure I'm at. Perhaps in this case, let's just go ahead and mark. Let's call this 25 degrees Celsius. The reason why I'm doing that is that this is considered room temperature in science. So when you hear room temperature, you might have your own personal feelings on what that means to you. But from a technical standpoint, room temperature is considered 25 degrees Celsius, which is about 78 Fahrenheit. So if we were at room temperature and we want to know what kind of phase will my substance be, we can use this graph to help us, because I'd locate, well, room temperature is here, and let's consider that my room is normal pressure. So what phase of matter is my substance will be where my normal temperature intersects with my normal pressure. And if we recall, normal pressure is 1 atmosphere. So that means if I go here and I go here, my substance is a solid. And this is how we would read a phase diagram. If I'm at a different pressure or a different temperature, I would look to where that would land among all the phases. So imagine that I cranked up my temperature. Since temperature is on the x-axis, we're going to be moving more towards the right, because every time my point moves right, I'm going higher on the temperature axis. So what's going to happen if I heat my solid? According to my phase diagram, well, it might be something that you expect based off of sort of common observation, right? Everyday observation. It's that we're going to end up at a point where we cross over the boundary between solid and liquid. So in other words, my conditions that made me solid before, so my normal pressure, normal temperature, I heat my substance, I'm now a liquid. And so what we're saying here is that this phase diagram helps us determine when we go through phase changes. And so we might say heat this to just arbitrary number 50. If we say, well, I didn't change my pressure, but I heated my temperature to 50, we see that we've gone from the solid area to the liquid area. And so this would be an example of a temperature change causes a phase change. And we might expect that because if I let my ice cube out and in sort of open air, it will melt. Solid turns to liquid. So it was at one temperature, it's warming up to a new temperature, and we see it on the phase diagram. So, I already mentioned, so what the line separates one phase from the other. What happens when we cross the line? When we cross the line, we go from one phase to the next. So we're going through phase changes here. So not only can we understand matter through our classifying in the beginning of the lecture, but now we can use a phase diagram to predict how matter will change physically under temperature or pressure if I push on it. So anytime I cross a line, it counts as a change of phase. So there are a total of 6 different phase changes that we can have on a phase diagram. So it might have, some of them we're familiar with, but others we might not be. What happens when I cross from solid to liquid? What do I call that? We might know it as melting, but the technical term for it is actually fusion. And you can use whichever term you'd like, but you should know what I'm talking about if I use the term, okay? So you should know what I mean by fusion, okay? If I go backwards, liquid to solid, that one's freezing. Technically solidification. What's the next one? 3. Liquid to gas is what I would get if I cross number 3. That would be called what? Boiling, or technically vaporization, turning to vapor. And to go backwards the other way, gas to liquid, what do we call that?
Condensation.
Yeah, condensation. Think like rain. A lot of water vapor in the air turns back to liquid. Condensation. Now the other two we don't have, we don't see as often in our everyday lives, though we do see it. When I go from solid to gas, that's sublimation. And when I go from gas to solid, that's deposition. Deposition is one that you could actually see in your homes, perhaps. If ever you, let's say, well, sometimes you don't have to do anything special. You come home from the market, perhaps, and you have some frozen food. You put the frozen food into your freezer, and then over the course of the day, the bag or container has a layer of ice on it. And you might ask, where did that ice come from? There's no water in my freezer. I didn't leave any. It's because when you opened your freezer door, you let some air inside, and that air, unless it's a very dry day, has humidity, has moisture in it. So when you trap that air inside your freezer, it actually deposits. It goes from the gas phase to the solid phase. And then you never see liquid water, but you get this sort of layer of ice that came directly from the gas phase. So that would be one example of it actually happening in real life. What do you need to know about the phases and phase changes? You need to know what the terms are. So melting, what does it mean? Going from solid to liquid and so forth. You need to be able to read the phase diagram to tell which phase change is happening. So if I said I'm at this point on my phase diagram and I go to this point, did I go through a phase change? If so, which one? And be able to tell me, okay, I went from gas to liquid, that's condensation. But also tell me whether or not you needed to heat something up or put pressure on it, right? Can I turn a gas to solid using pressure? Well, yes, you could, because if I move vertically from my gas to my solid phase right here, this vertical line would be pushing down on your gas until it goes back to solid. So being able to read the diagram just by points, so temperature axis, pressure axis, and telling me what's going on to the substance. Okay. Other key points on this diagram. We can always identify the normal melting point and boiling point of a substance from a phase diagram. What do we mean by normal? It means the same thing as it did before, as standard. And specifically, I should say at standard pressure, which, if we recall, is 1 atmosphere or 760 millimeters of mercury, since that's the conversion factor. So how do I tell what the normal melting point is for a substance? Well, I say normal means at standard pressure. So standard pressure is 1. So I am going to look across at the 1 mark. At what point does this substance turn from, according to what I want, from solid to liquid? That's melting. That's going to be here. This is where we cross the line. This will be called the normal melting point of the substance. At normal pressure, we cross the line here. So we would look down and say that temperature, which we'll call the melting point, is 60 degrees. We do the same thing for the boiling point. We look for normal pressure and we look where it crosses. So the normal boiling point of this substance is 140 degrees. Furthermore, we can actually get a little bit fancier with what we're doing. We mentioned crossing the boundaries, but what do you think happens when we're on the boundary? So for example, what if I'm right here on my phase diagram? What kind of substance do I have there? Anybody have a thought? Your thought is probably correct.
Mixture.
Yeah, so solid to liquid. So we imagine that if I went a little bit to the left, I'd be a solid. If I were a little bit to the right, I'd be a liquid. And in fact, if we're on the line, then we'll have both. So on-line mix of phases. So that's actually pretty pretty shocking, right? There's one special point that is actually of you know, a lot of interest. It's a fascinating point just for itself. It's actually the point you see at the sort of where all three lines meet. We call this the triple point of the substance. And that means we have the three phases of matter. So you might be asking, how does this work? And I believe that on this particular topic page in the module 3, I forget which page. I think that I posted the YouTube video. If I didn't, I will post it. But I posted a YouTube video of water at its triple point. So what does that mean? It means that someone was recording a video. What they did was they picked the exact temperature and the exact pressure and placed water in a container with that temperature and that pressure. So they actually needed to have a vacuum pump. So it was sucking the air out to lower the pressure. But if you're able to have the correct temperature and pressure to reach the triple point, what will happen is your water will actually cycle through all three phases of matter pretty much forever unless you disturb it. So in that video, you actually see the ice melts and then starts to bubble because it's boiling. And then the boiling steam actually turns back into liquid water and then freezes again. And it just keeps cycling through. It's a really cool video. Oh yeah, some people are saying they saw the video. Yeah, it's pretty trippy to see. But that literally will happen if you land on any of these boundaries. Each boundary represents having a mixture of different phases. So this one is going to be, if I'm on the line, I'm liquid and gas together. If I'm on this line, I'm solid and gas. And then the triple point, you have all three phases. Sometimes we like to focus on one particular curve. The boundary between liquid and gas is called the vapor curve. And so sometimes we put two vapor curves together to make conclusions. So as an example, we have the vapor curves for ethanol and water. So one thing we can ask ourselves about ethanol and water and answer from these vapor curves is which is more volatile. So volatile is a word we hear. What does volatile mean? Easily evaporates or easily becomes gas. Yeah, evaporates easily. So why does the vapor curve help us? Because the vapor curve is what tells us where our boiling points are. So if I take a look at these two vapor curves, I've put them together on the same graph now. Can we tell which liquid, ethanol or water, is more volatile by comparison? Which one is easier to boil?
Ethanol.
Yeah, ethanol. And maybe we know that from intuition, but we can prove it by saying, well, let's look at the normal boiling point. Again, it's where our curves meet. So for ethanol, that's about in the 70s, 70 degrees. But for water, it's about 100 degrees. So ethanol is much easier to evaporate and boil. So we would say ethanol is more volatile than water. And why is this important? We use it for yet another physical property that can be exploited for a physical separation. You may have heard about or maybe even had experience with distillation. This is a chemistry distillation setup. It has a few different parts. The container you see here is called a round bottom flask. It contains two liquids. In this example, it's ethanol or water. But what we're doing is separating by, and all separations exploit a difference in boiling point. I'll just say boiling point. Because we have two liquids with very different boiling points, ethanol boils at a much lower temperature than water. What's going to happen is that we'll put this, flask under a Bunsen burner, or maybe just start heating it with a heater. And the ethanol will begin to boil before the water. So the water remains as a liquid, but according to this, and again, we can prove it by saying, well, what if my mixture starts here? Well, when I move across by heating, remember the temperature scale goes left and right. As I'm heating it, my ethanol is going to boil first. So the ethanol actually travels up these tubes and goes into a condenser, which is a glass tube that actually is two tubes sort of nested in each other. The outer tube is connected to a pump, much like an aquarium pump, that actually pumps water through it. So water flows through the hollow portion of this tube and cools the glass down. When it does this, the hot ethanol vapor actually cools back down and becomes a liquid again. And so it's angled so that as it becomes liquid again, it drips back down and it goes into another flask. And we say that the separated liquid is called the distillate. So what we get at the end, that substance, is called our distillate. And that's how we use sort of our knowledge of observing nature, identifying properties, and having conversations about particles helps us out. We've seen a couple applications, filtration and distillation, where knowing about phases and knowing about how to classify matter helps us do something important. In fact, there are lots of other ways we can separate substances, and it all goes back to, well, can I observe a difference between the two? And so presumably what would happen is that at the second flask is purer. It probably won't be completely pure, but pure ethanol. And the first flask still has the water in it. And that's the hope, is that you're separating them from each other, in this case by a difference in boiling point. And so here we are at the end. I think we saved time because I didn't actually do the simulation. So I apologize for that. You didn't get to see the fun sort of particles bouncing around. But I'll try to get that working and post it. So what should we know? Matter comes in all shapes and sizes, and it's important to classify them in the different ways we've talked about. We should be able to predict what the atoms or molecules are doing based off of our classifications, or how they look, for example. And we describe matter through chemical and physical properties, and this information helps us separate them by knowing that, oh, ethanol boils at low temperature, water boils at high temperature. Oh, I can separate by distillation. Or, the example I gave a few slides ago with the heterogeneous mixtures, manganese 2 hydroxide does not dissolve in water. It produces a solid liquid heterogeneous mixture. It can be filtered, things like that. And then phase diagrams. We can alter matter, not just alter it, but we can manipulate it however we want by using a phase diagram. If I have a substance and I say, I want this substance to be a liquid, we have two options. We can change its temperature, or we can change the pressure pushing on it. So this is the power of what we're doing right now. Not only can we predict, we can observe, but we can control matter a little bit better by using these observations to our advantage. And that's what we're building towards, being able to describe matter and make those predictions and manipulate matter in good ways. Oh, and before we go, one last good question. Does boiling point have anything to do with density? So the two aren't, I would say no. However, I'm sure there's an exception to that. But typically things that are, I would say there's a correlation, but not a causation. And by that, I mean that more than likely something with a certain density should have a certain boiling point. But I'm not sure how connected, and I don't believe that density causes something to have a certain boiling point. But that's a good thought. In what ways are these properties connected? But we will definitely see that some properties are connected to each other. And that's going to happen in our chapter on the properties of liquids. We'll build our vocabulary of different properties, so viscosity, surface tension, and so forth. And those actually are connected because they're explained by a sort of similar explanation. So stay tuned for that. Okay, but this concludes our lecture. So I'm going to go ahead and stop the recording, and then we'll chat.